This is a USB wall outlet that is sold in many US stores for under $20. It is a generic MVMT brand, and the model number for this particular one is LA-2SA. And I think the more common version of this wall adapter has 3 main outlets instead of just 2, which arguably is more practical than this one, as these adapters are designed to plug into the standard duplex wall receptacles. And the 2 outlet version simply just replaces the 2 vertical outlets with 2 horizontal ones here, whereas the 3 outlets ones adds an additional one. And because these adapters are sold in US stores, they do have some kind of certifications. So I'm not sure if you can see this, but this one has an InterTech ETL stamp on it. So presumably it meets stricter standards than those no-name adapters that you can find on eBay. Now, this version claims to have 2 of these 2.1 amp, 5 volts charging USB ports. And let's do some quick tests to see if the claims are accurate. And for the testing, I'm going to use this small electronic load that I built many years ago. And of course, nowadays you can just buy one of those USB adapters that also serves as electronic load for the USB ports, which is quite handy, but I don't have any of those, so I'm just going to use this instead. And let me first plug this in, and we'll see what it does. And you noticed, you probably can't see it very clear because I have all the lights on, but as soon as you plug it in, there's a permanent blue LED lights up. I really don't like these kind of things because they cause a lot of light pollution, especially at night if you're trying to sleep and you don't want lights to be on. Unfortunately, a lot of the electronics nowadays have this kind of lighting to look cool. But this one, actually, interestingly enough, it says protected. So I'm not sure if it has any sort of protection built in, or it's just some kind of a gimmick and showing you that it's protected. But look at the slot here. This is actually where your phone's supposed to be placed in when doing charging. So that's kind of nice. Anyway, so let me plug this in and we'll hook up the electronic load. And for the load, I'm going to explain a little bit. So I actually built this adapter here, and basically it's really simple. It's one side is the negative, one side is positive, and this is where the power draw would be coming from this USB adapter. And so the idea here is I can hook up my measurement instruments on these soldered wire stubs here, and so that I can connect it up. For instance, let me just show you here. So I'm going to plug this in one channel, and that's the channel we're going to measure right now. So let me turn on the Keithley 196. Of course, I don't really need a meter of this caliber, but I thought I would just use this a little bit more, as in most of my videos I don't get to use this Keithley 196. So let's hook it up to the input voltage here. So as you can see that we're at 5.0368, which is accurate enough. Of course, we can always make it having even one extra digit. It's not necessary, but since we have it, why not? So the idea here is I'm going to hook up this BK Precision 2709 as my current measurement. So I'm going to do the 10 amp range, and as you can see that I have this slot here. So basically, this gives me the ability to hook in the amp meter here to measure the current. So when that is set, I also have this electronic load. So let me just show you here. Let me turn it on first. There should be a button somewhere here. Oh, I need to plug it in, of course. So the electronic load is on now, and so basically the load, I would just plug it onto these two leads here. So okay, so now we can see how this thing works now. So I'm going to start turning up the electronic load, and we'll observe the voltage and the current. Remember, this wall adapter is rated for 2.1 amp, so we want to see whether or not it can provide that current output. So now I'm gradually increasing, and I'm measuring the voltage after this cable, so we would expect some voltage drop. So this looks okay. So right now we're about just shy of half an amp, and we're at 4.9 volts, which is not a problem. So let's go to 1 amp, and the current regulation, the regulation of this wall adapter, and you can see that the voltage should actually increase a little bit. So now we're at 1.1 amp, and we're going to keep increasing this. So the voltage does drop down a little bit. So now we're at 2.1, which is the rated maximum current that it can supply, which doesn't seem that there's any problem. So which means that this one indeed can output 2.1 amp. Now, the question I have is what happens if we keep increasing the current? Ideally, after it exceeds certain numbers, that it should shut off the output current, so that the adapter itself is protected, and also the whatever is loading the circuit doesn't get overheated. So let's take a look. So now I am turning it up, and we are at 2.3. We're still okay. Now you can see that right as soon as we hit about 2.3, the voltage started dropping significantly, and if we just keep increasing, and it drops to 0, so the output is cut off. So actually this is great, because then it protects the circuit from the output short. So now if we remove the load, you can see that again the voltage comes back up. So which is working as exactly as it advertised. Now let's move it to the next channel. And I would expect that both channels are operate the same manner, but let's just take a quick look here. So let's ramp it up. And as you can see, yep, so both channels work exactly the same way. So it seems that at least from one channel perspective, this one absolutely can provide the 2.1 amp rated output current. So the next thing I want to see is what if we load both of these outlets with some load to see whether or not we can handle 2.1 amps in each channel. So for that, I'm going to put the electronic load on this one. It doesn't really matter. And also I made this this simple board with 1, 2, 3, 4 10 ohm resistors in parallel. So this would give us 2.5 ohm, and which is 2 amps. So it's just shy of 2.1 amp maximum current output. But the idea here is I'm going to use this to load up one of the output, and use the electronic load to adjust and see what type of current we can get on the other channel. So let's, okay, it would help if I plug in the right way. So let's plug this in. So now we're loading the first channel, and now let's adjust the electronic load. So we are at 0.5 amp. It's already started dropping. You can see this, it's already 4.4. So which means we probably, when we talk about this 2.1 figure, is really the combined output, not individual channel output, because right now you can see that we are outputting less than 1 amp, and it's already down to the 3.5 volt range. So you really cannot draw more than 300 milliamps from this channel, which the original one was drawing about 2 amps. So these, goes to about 2.3, which was what we measured earlier. So this is a little bit of a disappointment, because now if you have two phones, power-hungry phones, charging at the same time, neither of those would be able to obtain the maximum current, which would significantly slow down your charging time. Anyway, but nevertheless, it at least meets the what it says in the spec, the output current for at least one channel. And so let me now power everything down, and I wanted to open it up and take a look at the construction of this USB wall outlet. And I just removed the 4 screws here, and we should be able to open this up. And here we go. So now we can see the inside of this USB wall adapter, and by the first look of it, it's actually not all that bad. It's in fact, the PCBs look very, very nicely made. And let me zoom it in, and I'll show you some of the features here. So now we can see it a little better, and as you can see that the mains come in onto this vertical board. And we have a filter cap, and by the look of it, a MOV and a fuse, and heat shrunk together. Now, this is presumably what they mean by protected, but as you can see, it's really just a marketing gimmick, as everything is barely just minimum components here. And so by the look of this LED, probably is tapped somewhere from this board via a resistor, probably. I think I can see it down there, but that's what is driving that LED. And interestingly, we do have some high voltage cutout here, so that is a good thing. And certainly, to pass certain regulations, you have to have the circuit designed properly, like this. But we see that here we have 2 more footprints, and for the MOVs, but we only have this single one installed. So I'm wondering whether or not this is just to cut cost, or I really don't know, because technically speaking, you should really populate all these footprints, and the energy one single MOV can absorb is limited. So usually when you see some these protection circuitry, you would see multiple MOVs in parallel. But clearly here we are skimming it down and only have 1. But 1 is better than nothing, I suppose. Now, one thing interesting you see is that it doesn't seem that the mains earth is connected to anything here. And let me just wiggle this out. Yeah, as you can see that it's not connected at all. So clearly this is a little bit of a safety concern, as for consumer products, you really want to make sure that at least some of the metal exposed components are actually properly earthed. For example, the USB outer shell here, and when it's not earthed, you could potentially get a shock if the circuit becomes live for whatever reason, either malfunction or there's some leakage through some of the path here. But that said, probably the designers, after they designed this thing, decided that it's not necessary. And by the look of it, it appears that we also have a fully isolated DC-DC converter here, and we can see the large isolation slot here. So these are properly designed to prevent arcs from jumping over, and so maybe that's the reason. But still, it would be very nice if the metal casing at least is earthed. So now let me remove some of the screws and take a look at to see if we can identify something on this DC-DC converter here. So now I just removed the 2 screws, and we can later flip it over and take a look at the other side. But from here we can see that we have this full bridge rectifier coming in, and we have the filter cap on the other side. Now, the main business is done by this 7-pin, actually 8-pin, but we only have 7-pin outlet. So here we have, this is presumably the output MOSFET. But I actually couldn't find any datasheet on this particular model, but it's presumably very, very popular, these kind of a 8-pin package here, for handling this single chip DC-DC conversion. And so there's really not too much on this board at all. And as I mentioned earlier, this is a very, very nice separated portion of the AC side of the circuit, main side of the circuitry, and the low voltage side of the output here. So let's flip it over and take a look to see if we have anything else. And probably you can see there's not too much to expect here. And we have some inductor and presumably a fuse and a capacitor on the AC side. And the DC side, as you can see, this is where the converted down voltage comes out. So it comes right to this side. And we can see how wide this isolation is. This is a good safety precaution here. So by the look of the actual output here, and you can see that these two are indeed in parallel. So that's why when we were loading down one rail, the other rail could not provide any meaningful current anymore. So that's the reason, because these two are indeed in parallel. So it seems that the construction of this MVMT USB wall outlet is actually quite decent, despite some minor sacrifices made during manufacturing. Of course, it would be better if it had two independent outputs that can each handle 2.1 amps instead of just having a single rail that provides 2.1 amps that is shared across both of the USB outlets here. I also wanted to measure the power factor of this charger, which I forgot to do earlier. Now, judging from the circuitry though, it doesn't seem like it has any active power factor correction circuitry, so I would expect that the power factor would be right around 0.6, but let's take a look nevertheless. So now we have reassembled this USB wall outlet, and let me plug into this power meter, and let's get a reading of what the power factor is. So when I just power it in, it draws a little bit of power, which is expected because we have this LED that is running. Now let me plug in this 2.5 ohm load onto the 5 volt rail, so it would be drawing around 2 amps. And when the number stabilizes, we are going to check the power factor. And indeed, it's only 0.55 and give or take 5556, and that's exactly what I expected. As I mentioned earlier, these ones do not have an active power factor correction circuitry built in. Anyway, I hope you liked the video, and if you liked the video, please give it a big thumbs up, and remember to share and subscribe. I will catch up the next time.